Have you ever wondered what the universe is made of? This question has puzzled scientists and philosophers for centuries. The universe, vast and enigmatic, holds many mysteries, and one of the most intriguing ones is its very composition. What are the fundamental building blocks of everything we see around us and even of the things we can't see? Enter string theory, a bold hypothesis that seeks to answer this very question. It's a concept that might sound more at home in a music class than a physics lecture, but it's a theory that has the potential to revolutionize our understanding of the universe. String theory proposes that the universe is not, as previously thought, made up of tiny particles like atoms, electrons, or quarks. Instead, it suggests that the fundamental constituents of reality are even smaller entities known as strings. These are not strings in the everyday sense, but unimaginably small, one-dimensional strands of energy. These strings, according to the theory, vibrate at different frequencies. Just like the strings on a guitar or a violin produce different notes when they vibrate differently, these cosmic strings give rise to different particles. Electrons, quarks, and other particles then are simply different notes on a cosmic symphony played out by these strings. But string theory doesn't stop there. It also introduces the idea of additional dimensions. We're familiar with the 3 dimensions of space and 1 of time, but string theory suggests there could be many more dimensions that we're unable to perceive. String theory is a daring proposition, one that promises a unified framework that could reconcile general relativity, which describes the universe on a large scale, and quantum mechanics, which explains the behavior of the smallest particles. These 2 theories are the cornerstones of modern physics, yet they seem incompatible. String theory could be the bridge that brings them together. So, could vibrating strings smaller than atoms be the answer to the universe's biggest question? Only time and more scientific inquiry will tell. But one thing is certain, the universe's mysteries are far from being fully unraveled, and string theory is a fascinating piece of that cosmic puzzle. String theory didn't emerge from a grand plan, it appeared by accident. Imagine, if you will, the year is 1969. An Italian physicist named Gabriele Veneziano is fervently working to unravel the mysteries of particle physics. He is trying to describe the behavior of particles like protons and neutrons, those tiny building blocks of matter that make up everything we see and touch. As he delves deeper into his research, Veneziano stumbles upon something unexpected. He creates a formula that describes the scattering of 4 strings, a mathematical representation that will eventually become known as the Veneziano amplitude. But here's the twist. Veneziano wasn't trying to describe strings, he was focusing on particles. The concept of strings, these infinitesimal vibrating entities, smaller than atoms, electrons, or quarks, was a byproduct, an accidental discovery. Yet, this accidental discovery set the stage for a new understanding of our universe. Veneziano's formula became the foundation stone of what we now know as string theory. The idea that the fundamental building blocks of reality are not particles as previously thought, but strings. Picture, if you will, microscopic wiggling rubber bands, each vibration, each twist and fold, creating the myriad of phenomena we interpret as everything from particle physics to large-scale occurrences like gravity. The birth of string theory wasn't heralded with grand fanfare. It was an unexpected offshoot of an entirely different pursuit. But as physicists around the globe began to explore Veneziano's formula, they started to unravel the potential of string theory. They saw in it a unifying framework that could reconcile the contradictions between quantum mechanics and general relativity, 2 theories that underlie almost all of modern physics but often clash in their interpretations and predictions. And so, from an unexpected beginning, string theory began to take shape. It emerged not from a grand design, but from an accidental discovery, a testament to the unpredictable and exciting nature of scientific exploration. String theory didn't just stop evolving with Veneziano's accidental discovery. Instead, it embarked on a vibrant journey of growth and transformation over the next 50 years. This journey was marked by bursts of new ideas and deep insights, illuminating the dark corners of theoretical physics and leaving an indelible mark on our understanding of the universe. The 1970s were a particularly fertile period for string theory. The decade saw the emergence of a new form of string theory, known as superstring theory. This theory proposed that the universe is composed not just of strings, but of superstrings. These superstrings are thought to vibrate in multiple dimensions, adding a new layer of complexity to our understanding of the cosmos. Then came the 1980s, a decade that propelled string theory into the limelight. This was the era of the first superstring revolution, a period of intense activity and groundbreaking discoveries. Notably, it was during this time that string theory was proposed as a potential theory of everything, a single framework that could unite general relativity and quantum mechanics, the two fundamental pillars of modern physics. The momentum didn't stop there. The 1990s heralded the second superstring revolution, led by the physicist Edward Witten. Witten's work suggested that the various forms of string theory that had been developed over the previous decades were all connected, part of a broader framework known as M-theory. This was a game changer, hinting at a deeper level of unity in the universe than previously imagined. But the evolution of string theory didn't end with the close of the 20th century. Even today, it remains a vibrant field of research, with thousands of scientists around the world dedicated to unraveling its mysteries. They're tackling some of the biggest questions in physics, such as the nature of dark matter and the origin of the universe. And yet, despite these advances, string theory has also faced its share of challenges. Some scientists question its lack of testable predictions, while others argue that it's too mathematically complex to reflect reality. These debates are part of the process of scientific discovery, helping to shape and refine our understanding of the universe. Nevertheless, the evolution of string theory is a testament to the power of human curiosity and creativity. It's a reminder that our quest for knowledge is never ending, always pushing us to explore new frontiers and challenge our assumptions. So where does string theory stand today? Well, it's a bit like a novel that's still being written, a story that's unfolding in real time. There are chapters yet to be penned, discoveries yet to be made, and mysteries yet to be solved. Despite its challenges, string theory continues to evolve, captivating the minds of thousands of researchers worldwide. It's a journey that's far from over, a journey that promises to take us even deeper into the heart of the cosmos. But where does string theory stand today? As we navigate the sea of the unknown, string theory remains the lighthouse, guiding our understanding of the universe. However, its ultimate validation remains elusive. No experiment has definitively proven string theory to be the fundamental theory of nature. Yet the lack of empirical evidence doesn't diminish its importance. String theory, despite its challenges, has managed to pass countless theoretical and mathematical tests. It's like a complex jigsaw puzzle that we're still trying to piece together. We've managed to fit some pieces into place, revealing slivers of the grand picture. But many pieces are still scattered around, waiting for the right moment, the right perspective to fit in. The beauty of string theory lies in its inherent elegance, uniting gravity and quantum mechanics, two pillars of modern physics, into a harmonious dance. It offers a unique language, a new lens through which physicists can investigate the mathematics of the universe and solve problems that were once considered intractable. Despite the controversy surrounding its empirical evidence, string theory continues to inspire a new generation of physicists. Thousands of researchers worldwide are tirelessly working to unravel its mysteries, hoping that one day they might stumble upon an insight that brings us closer to the truth. It's important to remember that fundamental physics is a long game. Albert Einstein first predicted gravitational waves in 1915, and they were not detected until a century later in 2015. We may not have the technology or the understanding to fully test string theory now, but who's to say what the future holds? So, while the jury is still out on whether string theory is the ultimate theory of everything, its impact on theoretical physics and mathematics is undeniable. It has opened new doors, sparked fascinating debates, and challenged the very way we perceive reality. While we may not have definitive proof yet, the journey of discovery continues. Who knows what mysteries string theory might unravel next? String theory has left an undeniable imprint on physics and mathematics. This theoretical framework has not only provided a new language for physicists to describe the universe, but it has also offered fresh perspectives to mathematicians. The concepts derived from string theory have been instrumental in solving complex problems within theoretical physics. It's like a Swiss Army knife for physicists, offering a variety of tools to dissect the intricacies of the cosmos. In the realm of mathematics, string theory has inspired new areas of study. It's as if the theory has handed mathematicians a new set of brushes to paint their abstract world. But beyond the realms of physics and mathematics, string theory has also sparked public imagination. Through its mind-bending ideas, it has encouraged us all to question our perception of reality and the universe. Whether it ends up being the theory of everything or not, string theory continues to push the boundaries of our understanding of the universe's deepest mysteries.